Today we have Laplace transformation of e power at. According to yesterday's formula, it is 0 to infinity e power minus st into e power at dt. So here the powers, if we consider, it will be 0 to infinity e power minus common s minus a into t dt. Now if you integrate this, we get e power minus of s minus a into t upon s minus a is having a negative sign. Remember, this coefficient will be coming down in integration. So 0 to infinity. When you put infinity, the whole part become e power minus infinity by minus of s minus a, and minus in the formula plus e power 0 is 1 upon s minus a. Here, as you know, e power minus infinity is 0, your final answer is 1 upon s minus a. So Laplace transformation of e power at is 1 upon s minus a. Now the same question, instead of e power at you have e power minus at, then it is 0 to infinity e power minus st in the formula into e power minus at in the question. So this will become integral 0 to infinity e power a minus common s plus a into t dt. Now when we integrate this part, we will be getting e power minus of s plus a into t upon minus of s plus a, having the limit 0 to infinity as usual. When you put infinity, you will get again 0 and put a minus in the formula and have a minus in the denominator, so it become plus 1 upon s plus a. So Laplace transformation of e power minus at is 1 upon s plus a. Now let's go to the next one. Here in the sine at, you will get integral 0 to infinity e power minus st into sine at dt. Now put it down. Now e power minus st sine at dt, we use a formula in class 12, e power ax sine bx dx. It is e power x by a square plus b square, a sine bx minus b cos bx. Here a is minus s and b is a. So when you apply this formula, you will be getting e power minus st by s square plus a square. A is minus s sine at, and minus in the formula b is a cos at. Now apply the limits from 0 to infinity as usual. When you put infinity, the whole part becomes 0. Minus in the formula, e power 0 is 1. So you will be getting 1 upon a square plus a square into, here sine 0 is 0, but you have a cos 0 is 1, so it becomes minus a. So finally a by s square plus a square. This is the formula for Laplace transformation of sine at. Now Laplace transformation of cos at, when you see, one second, Laplace transformation of cos at, the answer I want, as usual, integral 0 to infinity e power minus st cos at dt will be writing, and here I will be using this formula in class 12, e power x cos bx dx. So this big formula, the derivation is there in another video. You can go through in class 12 derivations. So here also a is minus s and b is a. So that means e power minus st by s square plus a square. A is minus s. You have a cos at plus b is a sine at. Now you have a limit again from 0 to infinity. When you put infinity, this whole part becomes 0, minus in the formula, and when you apply 0, that become 1 upon a square plus a square, and here minus s into cos 0 is 1, sin 0 is almost 0. So it will become s times of 1 upon s square plus a square. So Laplace transformation of cos at is s upon a square plus a square. Now let's go to little higher order. When you go for sine square at, I use a formula sine square a is equal to 1 minus cos 2a by 2. This is the formula we have in class 12 again. So here sine square at is Laplace transformation of 1 minus cos 2 at by 2. By taking a linear property of Laplace transformation, I will get half outside. Laplace transformation of 1 minus Laplace transformation of cos 2 at, and this is having a whole bracket for half. You know the Laplace transformation of 1 as studies is 1 upon s minus, today for cos 80, let's go back from the definition. Cos 80 was s upon s square plus a square, but instead of 80 we have a 280, that means s upon s square plus 2a square, which is 4a square. Simplify this, you'll get the answer.